Okay, so recall the double angle identities. You really have to memorize all these. In the long run, if you go take calculus or something else, they'll expect you to know these. These were the sine of 2x. How do we get the sine of, I wrote A, actually, 2a. Comes out to be 2 sine A cosine A. You want to memorize this one by itself, but how do we deduce that? If you forget it, you can figure it out. I found that by figuring it out over and over, I eventually remembered this one very well. How did we prove this one? First, we said you have to memorize the sum and difference formulas, right? So you had this sum formula. You had the sine of A plus B equals sine cosine plus cosine sine. So you need this one too. This is used a lot in higher mathematics. Maybe this is your last course and it's more interested in the triangles, but if you do waves later, you need these sine and cosine functions. And so they're very important in other classes in physics and engineering and calculus and all sorts of other things. So we have this one, right? Sine of A plus B is sine cosine plus cosine sine, right? Remember that one? If you remember this one, just put B equals A and you get sine A cosine A plus sine A cosine A again. There's two of them, right? So that was the proof. That was how I was able to remember a lot. Maybe that doesn't help you, I don't know, but I thought if I could remember this one, then it's easy. I always figure this one out because you put A equals B in this one, right? And then pretty soon this one is something natural. Then you have this one, cosine 2A, right? Well, that's, remember that one? You want to memorize this, it's cosine squared minus sine squared, because on this next test, which by the way is coming up a week from Wednesday, right? So on this Wednesday, I'm going to hand you out, put out on C12 a list of practice problems you can start studying, and on Monday we'll do part of the class review, okay?
We're Tuesday, Thursday class.
I'm sorry, yeah, a week from, well, it's too early in the morning, yeah, Thursday of next week, sorry about that. Yeah, Thursday of next week is coming up, so you want, on Thursday of this week, I'll put out the practice problems on D2L, maybe before then, try to have them early. But watch for that then. Okay, so the cosine 2A is cosine squared minus sine squared. The way you can memorize that, sometimes I try and think two things at the same time. I always get mixed up. All right, so, but this comes from the cosine of some angles formula, right? Cosine A plus B, what was that formula that we memorized already? Oh, it was cosine cosine minus sine sine, right? On the cosine, plus goes with minus, where the sine plus goes with plus. So you put these in the same order. If you can remember this one, right? Put A equals B, cosine cosine A is cosine squared A, sine A is sine squared A. All right, so this was the proof. That's why I want to do the proofs on some of these. They really help you to remember and figure out the next ones, and it always stays better. And in higher mathematics, I always find out it just kind of goes away if I just rote memorize it. But if I figure it out, then it stays with me, and I can remember this and I can use it because I understand it. All right. So there was that one, and then there was a double angle formula for tangent. Tangent to A comes out to be 2 tangent A over 1 minus tangent squared A. And this one came from, what was the proof of that one? Tangent of the sum of two angles, right? Tangent A plus B, which was this section we just finished, is tangent plus tangent over 1 minus tangent. This one I have more trouble remembering because I didn't use it as often. Tangent plus tangent over 1 minus tangent. All right. So those are those three that you can figure out from the sum identities. And now you might think, well, if I can write a sine of a double angle in terms of a sine and cosine of a single angle, maybe I can write, write a single angle in terms of half that angle, right? And that's what we can do now. From these, we can now prove half angle identities. Let's call this 1, 2, and 3. Suppose we say from 2. Suppose we put say theta equal 2a, right? So that a is 1/2 theta by dividing each side by that. What do we get if in this one we put 2a equals theta? On the left, we have cosine theta. And on the right, we have cosine squared minus sine squared. Of a, where a is 1/2 theta, so this is 1/2 theta. And look, I've got a half angle identity. Cosine squared of a half theta minus sine squared of a half theta is given in terms of cosine of the whole angle, theta. Well, I've got two different trig functions in half theta, so maybe that's too many. How can I get rid of that? I know. I've got a Pythagorean identity. Probably use those a lot. I remember that sine squared is 1 minus cosine squared, right? So I could replace that using the Pythagorean identity and write this as cosine squared on the left. These are equivalent, right? Cosine squared 1/2 theta minus 1 minus cosine squared 1/2 theta. Using that Pythagorean identity, that sine squared of any angle plus cosine squared of that angle is equal to 1. If you subtract cosine squared from each side, you see that sine squared is 1 minus cosine squared, right? Or replace this sine squared with 1 minus cosine squared of the same angle, a or 1/2 theta. All right, and now on this side, I've got, let's see, cosine theta equals cosine squared minus cosine squared is 2 cosine squared is 1/2 theta minus 1. All right. Now I can solve that for cosine squared 1/2 theta. Suppose I add 1 to each side and divide by 2. All right. So then I add 1 to the left and get 1 plus cosine theta, and then I divide by 2, and I get that. I add 1 to this side, canceling this out, and divide by 2 and get cosine squared 1/2 theta. I did 2 little algebra steps there. And now if cosine squared is equal to this, then what's cosine? I'll switch sides now and take the square root. If cosine squared is this, suppose I say x squared equals 4, then x must be, well, it could be square root of 4, which this principal square root means the non-negative number whose square is 2. Or it could be minus that number, right? So we put plus or minus the square root of 4, which is plus or minus 2. This radical sign means the principal square root of the non-negative number whose square is 4. Same thing here. If cosine squared is equal to this number, which is non-negative, then cosine could be, depending on the quadrant, either plus or minus the square root of this number. So we'll switch this over here and say that cosine 1/2 theta, switching sides and square rooting, plus or minus the square root of this side, square root 1 plus cosine theta. I told you we'd learn a lot of algebras, right? There it is. There's a half angle identity. By putting theta equals 2a in the double angle identity, I derived a half angle identity for cosine, right? So we can call this equation 4. 1, 2, and 3 are double angle identities. Given the sine and cosine of an angle A, you can figure out the sine, cosine, and tangent of twice A. This one, given the cosine of an angle theta, you can figure out the cosine of 1/2 of theta, right? So I like some of these proofs because they show you the things we need to do also coming up, and I'd like to be able to do things kind of like that, maybe not quite that hard in general, but there are some very important equations. I'm going to erase this now because we don't need this anymore. All right, and now what about half angle identities for other trig functions? Like these three, we're only interested in double angle identity with sine, cosine, and tangent. The other ones have double angle identities, but they're not used very often. So usually you just take the reciprocals of these. If you want cosecant of 2a, you just take one with the sine of 2a, right? For instance. So same thing here on these half angle identities. I'm only going to do actually sine and cosine. I think I'll leave off. Well, we'll do tangent too. I was going to say just sine, cosine, and tangent, but tangent is almost an afterthought to this, right? So there's cosine squared. Now, how can I get a half angle identity for sines? Well, we'll say also from equation 2 with, just like we had here, theta equals 2a and a equals 1/2 theta. Let's write just what we did before, the same thing right here. Cosine theta equals cosine squared 1/2 theta minus sine squared 1/2 theta. In other words, we went back to equation 2, and again, I put 2a equals theta, there's cosine theta, and a equals 1/2 theta, and then cosine squared minus sine squared 1/2 theta, right? Now this time though, I'm going to replace cosine squared with 1 minus sine squared, again by the Pythagorean identity, right? Sine squared plus cosine squared equals 1. You're going to replace sine squared with 1 minus cosine squared, or you're going to replace cosine squared with 1 minus sine squared. Oops, 1/2 theta. So Pythagorean identity. Cosine squared is 1 minus sine squared, so the sine squared plus cosine squared. And then this one hangs on at the end. And now I've got 1 minus 2 sine squared of 1/2 theta, right? 1 minus 2 of these. And still cosine theta on this one side. For all equivalent statements then. Right, because I just use identities together. Now I can solve for sine of 1/2 theta from this one. So that's the trick. You take the double angle identity for cosine, put a equals 2a, and just solve and then solve for either sine of 1/2 theta or cosine of 1/2 theta. So this time I'll subtract 1 and say this is cosine theta minus 1 equals minus 2 sine squared of 1/2 theta. So now let's see, I could divide by -2 and get cosine theta minus 1 over -2 equals sine squared of 1/2 theta. And let's see, if I take minus the top over the minus the bottom here, then the top becomes 1 minus cosine theta and the bottom becomes plus 2. So we won't spend all our time on proofs, but I just wanted you to see that what the double angle identities by making this substitution give you the half angle identity. And now finally, if sine squared is this number, then sine must be plus or minus its square root, right? So sine 1/2 theta, square root of the right side must be plus or minus the square root of the left side if the two squares are equal. 1 minus cosine theta over 2. All right. So that could be equation 5. All these ones here that are numbered, you need to memorize. Trigonometry is full of things to memorize, I'm afraid. They are used a lot later. That's why you have to have them. So there's sine of half an angle. What about tangent of half an angle? I think tangent of half angle is not used all that much, and there are different half angle identities for tangent actually. Sometimes you'll see a different one. Just bear in mind, you may not see the same one every time. This is the most common one. Because it's not used so often, I just like to do this. What can I do to figure out tangent of 1/2 theta? Without all this work.
Since you already know the identities, do sine of 1/2 theta.
Yeah, there you go. If you can remember that, you can figure it out every time. That's how I remember this one. That's why I give this one to you. It's easier to memorize than the other one. If I just think, wait a minute, tangent is sine over cosine, right? Very good. And I already have half angle identities for that, right? So this is plus or minus the square root of 1 minus cosine theta over 2. That was sine of 1/2 theta. Divided by cosine of 1/2 theta is plus or minus square root 1 plus cosine theta over 2. Now you start to see these half angle identities are not actually so hard to memorize. You can write this now as a single square root. Right? Square root of the quotient is the quotient of square roots. Remember this from algebra? If you have square root u over square root v, with u and v both positive numbers, then that's the square root of u over v, right? You can write it as a single square root for any positive numbers u and v. And u can be 0 also. And so now we can put these 1 minus cosine theta over 2 all over 1 minus, 1 plus cosine theta over 2. And now the 2's cancel, and you get tangent 1/2 theta is plus or minus square root 1 minus cosine theta over 1 plus cosine theta. This proof is very important to see because it helps you to memorize it again. So that's the last half angle identity we need, is that one. If you memorize the first two, just take their quotient, this one over this one, and the 2's cancel, and you get this. It's really easy like that to memorize that one from the other two, and then we don't have to work so hard. So this is, I like this one to memorize, you can figure it out. And in all three cases now, all you need is cosine of the whole angle theta to figure out sine, cosine, and tangent of half the angle. How about that? That's kind of nice too. And you might think, oh, wait a minute, plus or minus, doesn't that cancel plus or minus? It does not actually, because the plus or minus depends on the quadrant, right? When I'm doing sine of half theta, when it depends on the quadrant that 1/2 theta is in, whether I get plus or minus. Those are different than the quadrants where cosine of 1/2 theta is positive or negative. Since they're different quadrants, when you take their quotient, sometimes this one's plus and this one's plus, sometimes this one's plus, this one's minus, this one's minus, this one's plus, they're both minus. So they can have any combination of signs. It's still plus or minus. They don't cancel because these vary according to different quadrants. So now we have finally the proof of all these three things. I'm going to erase these, although we're going to use them again. I need the board space. Maybe you remember from last time since we've already been studying those, and I'll remind you of these. Hence, we have in all the half angle identities. I think it's worth doing the proofs there because it really helps to remember them and see why they work. There was a real famous guy in particle physics. He got the Nobel Prize, Richard Feynman, and he used to have to always understand everything. And boy, it was great because he became famous. He was with Einstein, and those other people developing the atomic bomb and that sort of thing. And he was real Caltech, if I remember right. Anyway, somewhere in California, one of the universities there, and he had all sorts of famous videos, famous for Feynman diagrams and particle physics and so forth. So, but the big thing was, you know, he had to understand all this stuff. He took the New York State, what was it? Into the test now, famous math test, and he was the highest score in the state of New York on this test of mathematics aptitude. And the amazing thing was how far he was ahead of second place. He just a high score than the second place in the state of New York was. So, but he always said his IQ wasn't all that high, you know, but he did real well by understanding the mathematics that he did. All right, so he was a physicist who understood the mathematics and was then very successful. All right, so half angle identities are as follows. Putnam exam, that's the one I'm trying to think of in this such a hard mathematics exam. So the half angle identities are, we'll remember these four, sine of 1/2 theta. And these are not so bad because they're all so similar, right? It's plus or minus the square root of 1 minus cosine of the whole angle over 2. How do you get the cosine of 1/2 theta? Remember that one? We just did it. It's down here still. Cosine of 1/2 theta is the same thing, plus or minus square root 1 minus cosine theta over 2. Add this little bar here, change it to a plus. So it's the same one, just change minus to plus. That's it. And then how do you get tangent of 1/2 theta? This is how you can remember this one. You just take this one over this one. The 2's canceling because the square roots combine. Right? So we did the algebra to remind ourselves. You get plus or minus square root this one, the sine, over the cosine with the 2's canceling. There it is. So we'll say, I put stars there, but I'll put them here instead. There's equations 4, 5, and 6. It's only 1 through 6 today to finish all the homework. That's most of the theoretical stuff. Now I want to do some practical things. Can you do the homework? Some of these are kind of tricky. I want to make sure you can do them all. You can come out of this course and be successful in your next classes. A lot of these are very common things you see in all trigonometry textbooks there. Like this one here. Let me blow this up a little. You probably can't read it. Oops. This one. Okay. Maybe that's got it. How about this? This is number 2 on your homework. You probably have different numbers. Sine of 11 pi over 8. What find the exact value? You're not allowed to use decimals in your answer. All right. So first example is, what in the world is sine of 11 pi over 8? That's not a special angle. How can we do this when it's not a special angle? Well, here's the note. Maybe I should put it up above. We can now find exactly, evaluate exactly any trig function at half a special angle. I better move this. Any trig function. Hopefully you brought pencils so you don't have to scribble in your paper. I always wrote in pen because those pencils hurt my hand after a while. So, but then I had to scribble everything out every time I changed something. Engineers are better. They bring mechanical pencils out. Hurt your fingers so much. But any trig function of half a special angle. All right, special angle being multiple of 30 degrees or 45 degrees. If we can take a trig function of a special angle, we can take a trig function of half of that. Right, half angle identity, or half of that actually, or half of that, or half of that, right? So you can keep going if you want to do enough work. Ad infinitum, right? Forever. So now let's try this. The problem number 2 on the homework is to find the sine, oops, exactly, of 11 pi over 8. Not a special angle, right? We can do multiples of pi over 6 and pi over 4. Those are special angles, but 11 pi over 8, how do I do that? Wait a minute. It's sine of half of 11 pi over 4, a special angle, because it's a multiple pi over 4, 45 degrees, right? So because it's half of the special angle, I can do it exactly. And how is it? It's half of a special angle. I use a half angle identity. I'll say by the, if I think of this as theta, right? Sine of 1/2 theta is plus or minus the square root 1 minus, by equation 4, cosine of the whole angle, 11 pi over 4, all over 2, and I can evaluate a cosine of a special angle, right? So that's the idea. Is anytime you have any trig function actually of half of a special angle, you can do it by a half angle identity. So I expect you to do this on test. I'm going to give you a problem where you do a half of a special angle like this on the next test of week from Thursday. Right? Plus or minus. Now, what's the cosine of 11 pi over 4? The same thing goes on here. Hold on. As with the double angle identities, if it's an acute angle, then you write a triangle as easiest. But if it's not an acute angle, then you go to the unit circle. You can go to the unit circle for acute angles also, but you don't need to. I'll draw the unit circle and I say, where's 11 pi over 4? Right? Well, the whole rotation is 2 pi is 8 pi over 4. Right? That's 2 pi. I need 3 pi over 4 again. Here's pi would be this, and so 3/4 pi is 3/4 of a turn here. 3 pi over 4. Think of it as pi over 4, pi over 4, pi over 4. There's lots of ways to think of it. So there it is, and that leaves pi over 4 here, right? So 8 pi over 4 is 2 pi, and then 3/4 of a straight angle leaves 45 degree, 45 degree, 90 degree, right, triangle here. Well, we know what that looks like, right? This side, maybe I should draw it around so you can see it. is square root 2 over 2, right? Square root 2 over 2 on this side. And we observe that the coordinates of the point are minus square root 2 over 2 plus square root 2 over 2. So that's the cosine and sine of whatever angle gets you there, right? And it includes, so that would be 3 pi over 4 is the cosine and sine of 3 pi over 4. It's also the cosine and sine of 11 pi over 4. Any angle with its terminal rate has the same 6 trig functions because it goes by the same point here. So cosine of 11 pi over 4 is minus square root 2 over 2, and I've got plus or minus square root of 1 minus a minus square root 2 over 2, all over 2. How about that? And now I've told you before in this section, sometimes the algebra is harder than the trig. We're all going to learn our algebra real well. There's like 3 points off, at least 2, maybe 3 points off if you leave your answer like that on the test. Why would that be? That's the right answer. But it's not simplified, right? So you want to simplify that. What's wrong first? Sounds like a Dr. Seuss book. How many things are wacky here or something?
It would be 1 plus square root of 2 over 2, but then you, common denominators, it'd be 2 plus square root of 2 over 2 divided by 2.
I'm going to do this. I've got a minus. I don't want to leave that. And then I've got compound quotients. I've got a quotient within a quotient, right? So I got to get rid of all those. I'm going to rewrite this. And then I've got a plus or minus. I haven't decided which one it is. So there are at least 3 things wacky here, right? So let's see. Here's what you might do. You might say, well, 11 pi over 4 is in this quadrant. Let's see. Sine is positive in that quadrant. You don't go by that. You don't go by this angle here. You go by the original angle, right? 11 pi over 8. Where is that angle? Well, you can figure it out. 12 pi over 8 would be pi and a half. Right? This is 12 pi over 8 because that's 3 pi over 2. Pi over 2, pi over 2, pi over 2, if you like. So it's a little less than that. It's by here. Here's 11 pi over 8. It's in quadrant 3. Sine and cosine are negative there. So I'll say this is in quadrant 3. You don't have to draw this picture. I always just picture this in my mind. It's almost 3/4 of a turn, right? So you just leave that out. Just draw that in your mind. Okay, so quadrant 3 is all you need to know out of that. Quadrant 3, sine and cosine are both negative, so I'm going to do that. We'll put quadrant 3 here for the original angle, not for this one. This one was in quadrant 2 where sine's positive. Let's go by this, defining the sine of the original angle. So you put the negative here. Now I can put negative here, so there's one thing fixed. And now minus a minus you want to fix, so that's plus. Minus square root 1 plus. I guess I'll just write it out in little steps. I hate to write so many steps. You don't have to write this many steps on your paper, but too many times I find if I do 3 steps at once or something, people are confused. I wind up taking longer to put the 2 steps in later anyway. So let's continue it up here. And now, since there's compound quotients, the way you get rid of them is you multiply through by the least common multiple of all the denominators in the secondary quotient. So there's only one secondary denominator, that's 2 here. So I just have to multiply top and bottom by 2 to get rid of that quotient. Hopefully do it here. My selection of chalk is going down fast here. All right, so if I multiply top and bottom by 2, let's do it right here. Top by 2 and bottom by 2 by the same thing. I don't change anything, but I have to multiply the whole top and the whole bottom, so I don't change it. And now 2 times 1 is 2. 2 times this one is square root 2. So I've got minus the square root of 2 plus square root 2 all over 4. Am I finished? Almost. What can I do still? I get you to look at this on the homework at least. Man, that square root of 4, I can write square root of the quotient is the quotient of the square root. So I'll write minus square root of 2 plus square root 2 over square root 4. And once I write that, I can say, wait a minute, square root 4 is 2. Right? So there it is. There's the answer that I want. There is exactly the sine of 11 pi over 8.
What happened to the plus? Plus or minus.
Quadrant 3.
Oh, yeah, I took it off because I said quadrant 3, I'll get rid of it since we know it has to be. Since the original angle's in quadrant 3 and sine of an angle in quadrant 3 is negative, I changed it. For this particular angle, it becomes minus. So that's the idea. Depending on the angle you put in, it can be plus or minus. But once you know the quadrant, then you put the.
Is it gonna be plus and minus most of the time for both, or?
It will be plus or minus every time you use the formula, and then you'll have to decide what angle you put in, whether it's plus or minus. It'll be one or the other.
Okay.
All right, good. Now there's a real interesting thing that comes up here. Some of these angles, when you do it this way, seem to be a contradiction with the ones you already did. So this is a completely correct answer. This is what I want to see on your paper. But what'll happen is sometimes this simplifies further, actually, with algebra. But it's tricky algebra, and this further simplification isn't much further. I'm going to say leave it like that. So you can leave square roots and square roots, and I'll allow that on the test. All right, square roots and square roots are okay. But here's an additional note. Sometimes this seems to contradict something we've already done, but it actually doesn't. And here is my favorite example of that. Let's use the cosine identity. Suppose I wanted to calculate the cosine, we'll do it in degrees this time. Cosine of 15 degrees. Wait a minute, I now have two ways to do this, if you think about it, right? What was the way we did before to do cosine of 15 degrees?
Fraction addition.
Yeah, if this is a multiple of 15 degrees, we could say it's cosine of difference of two special angles, right? Any multiple of 15 degrees can be written either as a sum or difference or both of special angles. I could also call it 60 minus 45 or something like that, but just so the difference is 15 and it works, and these are special angles. All right, and then I have the formula for cosine of a difference of two angles. Cosine A minus B, right? Remember that is cosine plus sine. Minus goes with plus. So it's cosine plus sine. Do these too much, you start having dreams, and don't do that many. All right, 45, 30, 45, 30. There it is. All right, cosine plus sine for cosine of the difference of two angles. And now we know all these, right? And since these are first quadrant angles, instead of going to the unit circle, I'll just go to the special triangles and say we have these. Here's the 45, 45, 90 triangle. Square root 2 over 2, square root 2 over 2. But really what you do once you've done a lot of these, you picture these in your head and you don't have to write them. Cosine 45 degrees is adjacent over hypotenuse is square root 2 over 2, right? Same with sine, it's opposite over hypotenuse, square root 2 over 2. And now what's cosine of 30 degrees? Well, then I do the other triangle. I memorize this one in my head. And I say, well, 30 degrees is up here. This side is 1/2. The short side goes opposite the short angle, and the longer leg goes opposite the longer angle. The longest side, 1, goes opposite the right angle. All right, so cosine of 30 degrees is its adjacent side to the hypotenuse is square root 3 over 2. Sine of 30 degrees is its opposite side over the hypotenuse is 1/2. So there it is exactly by the difference identity. I got, remember, top times top over bottom times bottom gives me, and these combine, right? Square root, we have this property from algebra, square root A, square root B equals square root AB for any non-negative numbers A and B. So this is square root 6 on top over 4 on the bottom. And this one is square root 2 over 4. They have common denominator. So I write this answer as square root 6 plus square root 2 all over 4. There is an exact answer that I'd like to see in the test, on the next test. I'll ask you to do one of these 15-degree multiples using your sum or difference formula here, right? Now, wait a minute. Alternatively, I can get rid of this, right? Alternatively, the half angle formula, told you I can't do this at the same time. Alternatively, cosine of 15 degrees is cosine of half a special angle, right? It's cosine of 1/2 30 degrees. I could also use the half angle formula, couldn't I? For that reason. So any multiple of 15 degrees is also conquerable, if you like, by a half angle identity. So you can use either one. On a multiple of 15 degrees, you can use a sum of difference formula, or you can use a half angle identity, and they'll both solve it, right? So let's see, cosine is now by 5. This one was by the comment before we started. I didn't remember the thing, but it's the double angle identity. This one here by equation 5, a half angle identity, was plus or minus square root 1 plus cosine of the whole angle, 30 degrees over 2, right? You think of this as theta, 1 plus cosine theta over 2, right? Is the cosine of square root plus or minus square root of that is cosine of 1/2 theta. All right, so there's by equation 5. And now is it plus or minus? Easy, all right? 15 degrees is first quadrant. Go by the original one here, not the one on this side. Everything in the first quadrant is positive, so cosine in particular is actually plus. That's quadrant 1 for the original angle. All right. And it turns out in this case you had quadrant 1 anyway. You would have gotten the right answer by luck if you would have used this one. So use the original angle, and cosine in the first quadrant is supposed to be positive. And now I've got, let's see, what's cosine of 30 degrees? It's square root 3 over 2 over 1, or square root 3 over 2. So this is plus the square root of 1 plus square root 3 over 2 all over 2. And once again, I've got the problem compound quotient, so I multiply top and bottom by 2 to get rid of that denominator, right? This is square root, right? If I take the whole top times 2 and the whole bottom times 2, then I've got 2 plus square root 3 on top, 4 on the bottom. And now, again, square root of the quotient is the quotient of the square roots. So, all right, there's a square root of 2 plus square root 3 all over square root 4 is 2. And there's the answer. All right. Sorry, I'm almost getting behind. If you need to stand up for a second, I didn't want to switch boards for one thing here. Wait a minute. It's not the same. What did I do wrong? I just wanted to point this out. This is a good example. These are actually both right.
They are. You just, the first one's not simplified, and the square root of 6 and 2 are flipped.
Yeah, if you can actually simplify this to write it like this. I think this one's simpler because you don't have a square root of a square root. But I will take either answer on the test. You can do it either way, and I'm happy with that. The difference of angles formula, or sum of angles formula, or some of the other ones, or the half angle identities. If you do the decimal on your calculator, you'll see you get exactly the same decimal. These are the same, and with tricky algebra, you can rewrite this one as this one, or this one as this one. But it's just not worth it. So leave your answer in either form. I just wanted to point out that it will look like you get different answers on some of these if you identity, but it's the same. But it's actually the same. All right. So with that in mind, we can look at some of these other problems. See, we've got one problem done already. It's gonna be a long day today. I just want to do a few more of these to get comfortable with doing the homework here. Some of these start to get a little tricky. This one's really not. But I just want you to see the flavor of these, because when they don't ask them online, they're always a little different than what they'd be like on the test. Here's number 4. They say if cosine squared 40 degrees. So you want to see how to do these. Once you see one of these, then it's bad. This is an easy one. Minus sine squared 40 degrees equals cosine A degrees. What is A? What is it? You know, they messed up here, didn't they? They put degrees here, put degrees here again. Okay. Anyway, that's just technical. All right, so A is what? How many degrees? And it should go in here. The trick is to recognize these identities. I said you have to memorize them. Maybe I'll make some other tests to look like this, just so they're more like your homework. But the idea is that you have a double angle identity. This was equation 2. And you just have to have this in your head, we recall that cosine of 2a, cosine squared a minus sine squared a. So this section is both double and half angle identities. And, oh, wait a minute, if this is cosine squared minus sine squared, that looks familiar. If this is a and this is a in the identity, this must be 2a, and unfortunately, maybe I should use theta or something here. This is the way I wrote it, and then they used a in the problem, perfect. So let's call this theta then. So equation 2 with theta instead of a. I don't want to have two different definitions. All right, so this is theta and this is theta. Cosine squared theta minus sine squared theta must be cosine of 2 theta. This must be 2 theta. Oh, it's 80 degrees. Right? So you put a equals 80 and you leave the degree sign off because they wrote degrees afterwards to save you the trouble. Right? So a is 80. Cosine of double angle, 80 degrees, is cosine squared 40 minus sine squared 40. The single angle. All right, so those are those problems. They want, when they write this in the blank, they just want you to say in your mind, wait a minute, that looks like an identity that I saw before, right? Here's some more problems. Maybe we should do this one, huh? What's the tangent of 247.5 degrees? Can you guess how to do that one? Got an idea? How would I evaluate the tangent of 247.5 degrees? Exactly, because they said, they don't say put in a decimal, they say put in an exact answer. How is that possibly going to have an exact answer for a non-special angle like that? We got two ways. Either it's a multiple of 15 degrees and I use the sum or difference formula, or it's half of a special angle. Well, that's not a multiple of 15 degrees. It's got half a degree in there, right? So it must be I'm supposed to use a half angle formula, right? Another Dr. Seuss, for those people who like the Dr. Seuss children's book, right? Reductio eliminato. You eliminate all the things that can't be. The one thing that's left must be it, right? The only thing the only way we do an angle exactly that's not a multiple of 15 degrees is the half angle identity so far, right? So this is the tangent of half of something. It must be a tangent of half a special angle. Multiply that by 2, and I've got 495 degrees, right? This is 1/2 of 495 degrees. Is that a special angle, 495? Has to be a multiple of 30 and 45. It's not a multiple of 30, but it is a 0. All right, but 450 or 45 times 10 is 450. This is 450 and 45. Yeah, it is, right? This is 11 times 45 degrees. Sure, turn up, it's a multiple of 45 degrees. It's a special angle. I can do this, right? 1/2 of the special angle. Okay, well, 11 times 45 degrees is 495. So we can do this one by the half angle formula. How are we going to do it? So the tangent is plus or minus the square root of 1 minus cosine of the whole angle, 495, or 1 plus the cosine of the whole angle, 495. The half angle for sine divided by a half angle for cosine with the 2's canceling. Right? There it is. So I just all I need is the cosine of 495 degrees. To do all these half angle identities, if you look at them here, 4, 5, and 6, right? All you need is the cosine of the whole angle. So that's all I need. 495 degrees I can do on the unit circle since it's not a acute angle to use with a triangle. So I say, well, there's 360. Now I've got 135 more, right? Oh, same angle as before, right? 90, 450, 45. Right? Halfway through this quadrant makes 450, 495. All right. And now that leaves me a reference angle of 45 degrees. Sure enough, a special triangle here. Work on, I figure out the side lengths here is square root 2 over 2, square root 2 over 2. And the cosine is the x coordinate. All right, cosine of 495, oops, must be minus square root 2 over 2, the x coordinates. Right? After all the coordinates are minus square root 2 over 2, plus square root 2 over 2 give you the cosines. So I'll put that in. I'll say exactly the tangent of this is well, wait a minute, is it plus or minus? How about that? Now, this isn't the angle you look at, right? Because that's double the angle. You look at the original angle. And so 247.5, here's 180. Here's 270. It's between those two. It's in quadrant 3, right? So this is in quadrant 3. In quadrant 3, tangent is positive, actually, right? Because sine and cosine are both negative, and tangent being their quotient is positive. So we're going to choose the plus sign. That's quadrant 3. Quadrant 3, not for this angle, but for the original one. All right, so we've got square root 1 minus, and let's see, cosine of 495 was minus square root 2 over 2. Be careful with your minuses here. There's always minus, 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 minus everywhere. 1 plus minus square root 2 over 2. I'll write it out like that. Okay. Now, how do I get rid of the compound quotients? Well, I can multiply through top and bottom by 2, right? So let's see. Multiply the top by 2 and the bottom by 2. I have to do the whole thing. And that won't change the quotient. And now the top is 1 minus, a minus is plus. And then 2 times 1 is 2. 2 times square root 2 over 2 is square root 2. And on the bottom, 2 times 1 is 2. 2 times minus square root 2 over 2 is minus square root 2. And I get that. That won't do either for a different reason. We said this last time. What's wrong with that? Yeah, it's not simplified because square root in the denominator, right? Remember when I have an a plus b square root c or a minus b square root c in the denominator, I want to get rid of it by multiplying the numerator and denominator by the conjugate of the denominator. So this is a minus b square root c. I want to multiply top and bottom by a plus b square root c, and it will get rid of that square root at the bottom. So what I'm going to do now is going to say, write the same thing, 2 plus root 2 over 2 minus root 2, and multiply the whole top by the conjugate of the bottom, 2 plus square root 2, 2 plus square root 2. And once again, let's see, square root of, here's what I recommend for the top. I used to multiply this out and get myself in all sorts of trouble, but think of it as 2 plus square root 2 squared when you have a square like that, right? I'll just keep it that way, 2 plus square root 2 squared. And the bottom now, if I multiply it out by 4, 2 times 2 is 4. 2 times minus square root 2, 2 times plus square root 2, it'd be 2 square root 2. First, outside, inside, it's just all possible pairs. Minus 2 square root 2. And last, minus square root 2 times plus square root 2 is minus 2. There it is. And if you did this right, if you multiply top and bottom by the conjugate, the square roots will go away. In fact, you don't have to write those if you want. You just write 4 minus 2. The bottom is just reduced to 2. So this is the square root of 2 plus square root 2 squared all over 2. How about that? What can you do with that? No?
I was gonna ask if I could see the other half of the board, that's all.
Say again?
The right side, just go on.
Okay, I was standing in front of it, I guess. All right, thank you. So square root of the square reduces to what's in there, right? Square root of 2 plus square root 2 squared is 2 plus square root 2. That's the square root of the top, and then square root of the bottom is square root of 2. Can I do anything more?
Yeah.
Yeah, this actually reduces. So you don't want to leave it like this. This is a messy answer, right? I want to simplify. It's 1 or 2 points off for that. I can rewrite this as 2 over square root 2 plus square root 2 over 2, right? Or 2 over square root 2. By algebra, right? This over this plus this over this is the quotient that I have here. What is 2 over square root 2? Well, this is equal to, I'm going to do lots of steps here. This is two can also be written as square root of two, right? And square root of two over square root of two is one. So rewrite two as square root of two, and now you write this as one. And now wait a minute. This is square root of two plus one, usually written in the other order, one plus square root of two. You do not have to write this many steps. I wrote a lot of steps here. But look how much simpler that answer is than this, right? So you want to simplify it. We'll mark off if you don't do that. Not a lot. Mostly I want to see you can get to here, but I'll mark something off. Okay? I told you these problems are harder than the algebra, yeah, than the trig.
So why is it a plus exactly, not a minus? No, on the,
Over here, yeah. What we're trying to find is the tangent of 247.5 degrees, and that's in quadrant three. It's between 180 and 270, this is.
yeah,
And so it's in the third quadrant. And
So
in the
that's gonna
third
be
quadrant,
positive?
tangent is positive.
then how come you put negative square root of 2/2 if it's positive?
Oh, because cosine of, then now I'm calculating
Oh.
495, so I go around to this angle in quadrant
Alright.
two, and the cosine in this quadrant is negative, yeah. So, yeah, so it's tricky, yeah, that's very tricky. That's why I'm making such an emphasis here. This happens on every exam. Somebody finds the quadrant of this angle instead of this one, or this one instead of this one. It's like the old shell game, right? It's put the ball into one of the three shells and switch them all around, which one's another. Oh, fun. The good thing is, when you're all done with the test, if you worry, maybe I got the wrong answer, how can you deal with this? Some of your calculators will do these exactly for you and get the answer. I want you to be able to do these by hand because there are theoretical calculations in your next class that require this without the angle known, and you have to put it in terms of square roots of the unknown angle kind of thing. But nonetheless, you can, on some calculators, you bought the expensive, hard to use one, it will tell you 1 plus square root 2 on that, and you can check it. But even if it doesn't matter. Put 1 plus square root 2 on your calculator that doesn't do these exactly, see the decimal, take tangent of 495, whatever it was, exactly, and see if it gives the same decimal. So you can check it on any calculator to see if this is the same decimal as when you take tangent of the angle. Sometimes you say, oh, I missed my minus sign, and fix it, right? So check your answers when you're done by running them in the calculator, see if it's the same decimal. I like to tell my classes when I was young, they sent this, I think it's a Terra satellite, I can't remember, this big satellite up, and somebody made a trig error, didn't convert it. And they wound up having to blow the missile up and lost the satellite because they made a trig error in this. Check those things when you're done. All right. Here's a good one. I think we did this right at the end last time, but it bears repeating. If I did, I think this is what I had right at the end. Suppose there's some problems like this that come along occasionally. Simplify sine 2a over cosine a. How can I simplify that? We were doing identities before, and what we said is on these identities, when you get these complicated trig expressions, often the identities will simplify them. Just wanted to point out when you do this section's homework, if you haven't done it, some of it already maybe, because we did double angles before, right? You take those three rules we did for the previous section and add to them, and whenever you see more than one angle, here's 2a and here's a, the first thing you do is reduce it to one angle. I called it rule 4, but you can put it first if you want. So the first, somewhere along the line at least, you try to get one angle, and that's one of the rules for simplification. Right? So when you see simplify, if you see more than one angle, reduce it. What's the sign of a double angle? This is what somebody's going to put in the test. It's 2 sine A, just pull the 2 out. That's wrong. What is it? Doesn't come out. It's like taking square root of 2a and say, oh, that's 2 square root a. No, it's not. You can't pull it out of the square root. You can't pull it out of the sine function either. Sometimes it's confusing because the book will write it like that to avoid parentheses. But just to be simple, but it's actually the sine function of, just like square root of. You can't pull the 2 out. the double angle identity for sine of two A is two sine A cosine A. So you have to have that memorized for the test, so you can simplify these, right? Ah, now I can see it clearly, right? Cosine cancels cosine. This is a fancy expression for two sine A. Despite how complicated you think this graph is, if you actually plot A versus y equals sine 2A over cosine A, what does it look like? Oh, it's just the sine function, the standard one, double height. So you just draw the usual sine wave, make it go between plus and minus 2. And this messy function actually simplifies to just this wave that repeats every 2 pi units because it's a sine function, just doubled in height, goes between plus and minus 2. There it is. So this simplification is very important in lots of applications. You realize, hey, this is just a sine wave, that's all this is. So be able to simplify by recognizing, first thing you do when you're simplifying is a double angle is use the double angle formula to get one angle. Right now it's sine and cosine is just A. Now you see I can cancel, right? So be able to do that. And some of these are kind of tricky. Oh boy. Let's look at 8, I guess. Do this one, but maybe I'm looking at it again and thinking maybe we need to. If there's one like this, I was going to do sine of the fourth of x, cosine of the fourth. Sine
It's
fourth power of
cosine.
x.
It's cosine squared.
Oh, I'm sorry. Yeah, reading too far from the side. Thank you. I'll get the wrong answer. Cosine squared sine of the fourth equals a plus b cosine 2x plus c cosine 4x plus d cosine 2x. Well, what a mess, huh? Plus d cosine 2x cosine 4x. Then a, b, c, d equals what? How about that? This is essentially a simplification problem, just a very convoluted one. There's a lot of ways to actually go about doing this, and I'm not sure I'm going to show you the easiest way here. Sometimes they have a particular way that's real fast on here that I don't recognize yet. But what always works is you say, get one angle, right? And out of this thing, if you want to get cosine squared sine of the fourth, we're going to have to make this all collapse, right? So the thing about these is you can work both ends towards the middle. Well, let's try this. One thing to notice is when you have a quadruple angle, the first thing you do is you rewrite it as a double angle formula. Cosine 4x is cosine of twice x, right? Double the angle 2x. Now, what do you do with that? You can say cosine of a double angle, think of this as 2 theta, is what? It's cosine squared theta minus sine squared theta, right? So this is cosine squared theta minus sine squared theta, right? Theta. But now theta is 2x. So it's cosine squared 2x minus sine squared 2x. Aha. Now I'm getting somewhere. So I can write this as plus d times cosine 2x times cosine squared 2x sine squared 2x. If you don't get every one of these, that's all right. It's a, you know, don't spend too long in these problems. The homework problems individually not worth that much. But now we've got it down to double angles instead of quadruple angles. But the idea is eventually I have to get it down to single angles, x. So there's the D part. Now here's also a cosine for x. I can do the same thing. It's cosine squared minus sine squared. Maybe I should have, let's see. No, let's just, all right. So this is plus c times cosine squared 2x minus sine squared 2x. And then b is cosine 2x. And then I've got a, there we go. So it all boils down like that. Now I've got all double angles, right? And I've got to get this down to single angles, cosine to a power times sine to a power, right? So how can I do that? Well, now you can use your double angle formulas to get them down to single angles, right? So, I can do this, I'll write this as A plus B times, let's see, cosine 2x is cosine squared x